Hello friends, we have learned about the band structure of silicon, germanium and gallium arsenide. There is an important difference between gallium arsenide and silicon or germanium. In gallium arsenide, both valence band maximum and conduction band minimum is located at the gamma point. This is known as direct bandgap semiconductor. In silicon and germanium, valence band maximum is at the gamma point, while conduction band minimum is not at the gamma point. In case of silicon, conduction band minimum is near the X point, and in case of germanium, conduction band minimum is near the L point. Silicon and germanium are called indirect bandgap semiconductor. Consider an electron being excited from the valence to the conduction band via photon absorption. In the process of photon absorption, both energy and momentum needs to be conserved. If we consider absorption of visible light having wavelength of lambda, then wave vector of photon is equals to 2 pi by lambda, where lambda is of the order of 5000 angstrom. Now let us try to get some approximate estimate for the change of wave vector of the electron getting excited from the valence band to the conduction band. For example, consider this case. An electron is getting excited from this point of the valence band to this point of the conduction band. In the process, wave vector of the electron is changing by this much. Thus, change of wave vector of electron is equal to, in this case, we find that this is approximately equal to the dimension of the first Brillouin zone, that is 2 pi by A, where A is the lattice parameter, which is of the order of 5 angstrom. Thus, momentum of photon 2 pi by lambda is very small compared to the momentum change of electron getting excited from the valence to the conduction band, that is 2 pi by lambda is much smaller than 2 pi by A. In case of a direct bandgap semiconductor like gallium arsenide, the electron is getting excited from this point to this point. In this case, momentum conservation is not an issue because K photon is negligible, and energy conservation is E gap is equals to h bar times the frequency of the photon absorbed. In case of indirect bandgap semiconductor like silicon or germanium, an electron at this point in the valence band is getting excited to this point in the conduction band. The energy of the electron changes by Eg, and the momentum of the electron changes by Kc. In this case, momentum conservation is not satisfied by momentum of the absorbed photon, which has negligible momentum compared to the momentum change of the excited electron. In this case, a phonon is also involved. Phonons are quantized modes of lattice vibrations. They have a large wave vector which is of the order of kc, as required to satisfy the momentum conservation. Thus, momentum conservation is taken care by the phonon absorption. Energy conservation equation is this. On the left hand side, we have energy of the absorbed photon, which is equal to the band gap Eg plus energy of the absorbed phonon. Phonon energy at room temperature is 30 millielectron volt, which is very small compared to the band gap. In summary, in case of indirect band gap semiconductors, photons give required energy and phonons give required momentum for an electron to be excited from the valence band to the conduction band. So far, I have discussed about the band structure of semiconductors in detail. At 0 Kelvin, semiconductors are insulators because the valence band is completely full and conduction band is completely empty. At finite temperature, some electrons are going to be excited from the valence to the conduction band, making both of them partially occupied. As a result, such partially occupied bands take part in electronic transport process. Let us find the number of electrons excited from the valence to the conduction band at some finite temperature T. Probability that an energy level of energy E is occupied at the conduction band is given by Fermi-Dirac distribution. This is equal to 1 divided by exponential E minus mu divided by kBT plus 1, where mu is the chemical potential, kB is the Boltzmann constant, and T is the temperature. This black thick line shows the Fermi-Dirac distribution at finite temperature. How do we find the location of mu? Note that if we put E equal to mu in this equation, then we get f of E is equals to 0.5. Thus, at E equal to mu, Fermi function is 0.5. From this, we can easily locate the chemical potential mu. Note that if band gap is not too small, then E minus mu is much larger than kBT. In this case, the exponential term is very large compared to 1. That is, exponential E minus mu divided by kBT is much larger than 1. Thus, we can approximate the Fermi-Dirac distribution as e power mu minus E divided by kBT. We use parabolic band approximation such that density of states is given by this expression, where m E star is the effective mass of electron and EC is the energy at the conduction band edge. Electron concentration in the conduction band at some finite temperature is given by the integral of density of states times the Fermi function. This integral is equal to the area under this blue shaded region. Putting the value of density of states and Fermi function, we get n equal to 1 by 2 pi square to m e star by h bar square whole power 3 by 2, and we use this expression for the Fermi function such that we get e power mu by kBt integral EC to infinity E minus EC whole power half exponential minus E by kBt d. Evaluating this integral, we get n equal to 2 times m e star kb t divided by 2 pi h bar square whole power 3 by 2 e power mu minus EC divided by kBt. Now, let us find the equilibrium concentration of holes in valence band. First, note that hole distribution function is related to the electron distribution function by F hole is equals to 1 minus F electron, such that we get 1 by e power mu minus energy divided by kBt plus 1. Now, if band gap is not too small, then mu minus E is much larger than kBt, and we can approximate FH by this. We can do this because under this condition, the exponential term becomes much larger than 1, and we can ignore the term 1. We use parabolic band approximation such that the density of hole states is given by this expression, where mh star is the effective mass of holes and EV is the energy at the valence band edge. The hole concentration in the valence band at some finite temperature is given by the integral of density of states times the Fermi function for holes. This integral is equal to the area under the red shaded region. Putting the value of density of states and FH, we get P is equals to 1 by 2 pi square to mh star divided by h bar square whole power 3 by 2 times e power minus mu by kBt. Keep in mind that we are using this expression for FH. Integral minus infinity to EV minus E whole power half exponential E by kBt dE. And evaluating this integral, we get P is equals to 2 times m star kBt divided by 2 pi h bar square whole power 3 by 2 exponential EV minus mu divided by kBt. So we got the expression for N and P. Let us multiply and find the expression for NP. This is what we get from these two terms. And if we multiply e power mu minus EC by kBt and e power EV minus mu by kBt, then we get e power minus EC minus EV by kBt, but EC minus EV is equal to the band gap. That is, this term is equal to e power minus EG by kBt. Thus, we got an expression known as the law of mass action, which is independent of chemical potential mu. Note that nowhere in the derivation we assume the semiconductor to be pure or intrinsic. Thus, the law of mass action works for pure as well as impure semiconductors. As long as distance of Fermi level from the band edges is large compared to kBt, the result holds good. At 300 Kelvin, NP in silicon is of the order of 10 power 19 centimeter to the power minus 6. In germanium, NP is of the order of 10 power 26 centimeter to the power minus 6. And in gallium arsenide, NP is of the order of 10 power 12 centimeter to the power minus 6. Comparing with the band gap values, clearly NP depends on the band gap. Lower the band gap, higher the value of NP. Note that NP changes by several orders of magnitude as band gap changes by a factor of 2. In an intrinsic semiconductor, number of electrons is exactly equal to the number of holes, because thermal excitation of an electron leaves behind a hole in the valence band. We can write NP is equals to Ni square is equals to Pi square, where the subscript I stands for intrinsic. From law of mass action, the intrinsic carrier concentration is given by this expression. Note that intrinsic carrier concentration depends on T power 3 by 2 as well as exponential minus Eg by 2 kBt. Obviously, exponential dependence dominates, and if you plot log of Ni versus 1 by T, you get a straight line. Note that Ni values for silicon, germanium, and gallium arsenide differs by several orders of magnitude. Now, intrinsic carrier concentration also has exponential dependence on Eg, the band gap. This explains the orders of magnitude change of carrier concentration due to change of band gap by a factor of 2. Since in an intrinsic semiconductor, electron and hole concentrations are equal, let me equate the two terms. Electron concentration is which is equal to the hole concentration. We can write e power mu minus Ec plus mu minus Ev by kBt is equal to mh star divided by me star whole power 3 by 2. And now taking logarithm on both sides of the equation, we get 2 mu minus Ev plus Ec divided by kBt is equals to 3 by 2 log mh star divided by me star. Now Ec, that is the energy at conduction band minimum, minus Ev, which is the energy at the valence band maximum. This is equal to the band gap, which implies that Ec is equals to Eg plus Ev. Replacing this in this equation, we get 2 mu minus Ev, and in place of Ec, I write Eg plus Ev is equals to 3 by 2 kBt log of mh star by me star. And finally, we have mu is equals to Ev plus half Eg plus 3 by 4 kBt log of mh star by me star. Thus, at t equal to 0, mu is equals to Ev plus half Eg. That is, mu lies in the middle of the band gap. If electron and hole has equal effective mass, that is mh star is equals to me star, then the temperature dependent term is always equal to 0. Then mu always stays in the middle of the band gap at any temperature. Otherwise, if mh star is not equal to me star, then mu depends on temperature. As a result, mu shifts from the middle of the band gap at finite temperature, as shown here. Remember that effective mass depends on curvature, and the electron and hole effective mass will be equal only when valence band and conduction band has same curvature. Let me summarize the most important points discussed in this lecture. Law of mass action is a relation between concentration of electrons and holes in a semiconductor under thermal equilibrium. Note that N is the electron concentration and P is the hole concentration. This expression is true for a pure or intrinsic as well as an impure or extrinsic semiconductor. In a semiconductor, N times P is always equal to the square of the intrinsic carrier concentration. This is the expression for intrinsic carrier concentration. Note that intrinsic concentration depends on T power 3/2 and it also has an exponential temperature dependence. The exponential part dominates and we get a straight line by plotting log of Ni versus 1/T. This is the expression for electrical conductivity. Note that sigma depends on carrier concentration as well as mobility. Now, mobility depends on T by a modest power law. As a result, temperature dependence of conductivity is dominated by temperature dependence of carrier concentration. And if we plot log sigma versus 1/T, we get a straight line like this.